Okay, so let's look at an example of determining whether a function is differentiable. So determine if this function f of x is differentiable. So if I'm trying to figure out if something is differentiable, I need to first check, is the function continuous? And then if it's continuous, I need to check if yes, do the slopes match from left and right? So, and one thing we'll discuss more later is polynomial functions. So all these nice friendly functions, they're differentiable everywhere. So with a piecewise function, we really just need to check, is it differentiable at x equals 4? Because it's definitely differentiable everywhere else. We are allowed to assume that. So if I'm checking if it's continuous, with proper notation, that means that I need to check the limit as we go to -4 from the left has to equal the limit as we go to -4 from the right, has to equal f of -4. That's the easiest one to forget. Has to be defined at -4 to be continuous. So let's go ahead and check this first. So the limit from the left of f of x, so since it's following the path of this parabola until we get to -4, that means its limit is just this expression evaluated at -4. And that is 16 minus 64 plus 2, -46. And the limit as we go to -4 from the right, again, since f of x is just following the path of this line, 8x minus 14, when x is greater than -4, then as x approaches -4, it's going to be very close to this line, and that also equals -46. And I just need to really quickly check f of -4 is also 8 times -4 minus 14, -46. So it is continuous. So now I need to check if it's differentiable. And checking if it's differentiable means I need the limit as x goes to -4 of the derivative from the left to match the derivative from the right. So this is checking if the slopes match, because this is the slope from the left. And then this is the slope from the right. So we'll do the one from the right first. So the limit as x goes to -4 from the right of the derivative. Now I could work this out using the limit definition, but we know some things about derivatives. 8x minus 14 is a line with a constant slope of 8. So its derivative everywhere equals 8. It is just a line with constant slope of 8. So the derivative of a linear function is always just whatever the slope was. So now the other one is going to take some work to figure out. So the limit as x goes to -4 from the left of f prime of x. So that is going to be approaching whatever this derivative is at x equals -4. So that's going to be the limit as h goes to 0, -4 plus h squared plus 16 times -4, -4 plus h plus 2. So that is my f of a plus h. And then we already calculated that f of -4 is -46. So this becomes minus -46 all over h. And I'm going to write this as, this is f of -4 plus h, and then that is f of -4. So we're subtracting f of -4. Those two subtractions will turn into addition, of course. So -4 plus h squared, that comes out to h squared minus 8h plus 16, because I write out -4 plus h, and then I distribute, and then distribute the 16 here, and I get minus 64 plus 16h, and then I still have my plus 2, and then I'm adding 46 all over h. Equals, limit as h goes to 0, and I'm trying to demonstrate good notation here by writing the limit every time. Now I need to combine like terms. And remember, anytime you're working out one of these limit definitions, I know it has to get something where everything on the top that doesn't have an h needs to go to 0. So whenever I do these, I look for the things that don't have an h. So it's this one, this one, this one, and this one. And I add those up first, because if those don't go to 0, I made a mistake somewhere and I need to go back. And in full disclosure, I stared at this problem for about 5 minutes before making the video, and eventually realized that 16 times 4 is 64 and not 48. But I knew I was doing it wrong because I wasn't getting the numbers to cancel out on the top. And this one, the 46. All right, so that's everything that doesn't have an h on it. So 16 minus 64 plus 2 plus 46, that does in fact go to 0. So I will continue. 16 minus 64 plus 2 plus 46. So 2 and 46 make 48. So that does go to 0. So then I'm just going to combine the rest of the terms. H squared minus 8h plus 16h. I have h squared plus 8h all over h. Now that I have everything that doesn't have an h did cancel out, so I have the limit as h goes to 0 of h plus 8. Now I can substitute, and that is 8. And that is the same derivative I got here. So f of x is differentiable because it's continuous f of x is continuous at x equals -4, and the limit as x goes to -4 from the left of its derivative is equal to the limit as x goes to -4 from the right of its derivative. And everywhere else, it's a polynomial, and polynomials are differentiable everywhere. All right, I hope that helped clear some things up about how to determine if something is differentiable. and had the added bonus of another limit definition of a derivative example. The nice thing is, pretty soon we will learn the shortcuts for working out derivatives like x squared plus 16x plus 2 and so forth. So questions like this become much easier once we get the shortcuts. But the concept is not going to change, right? So I'm going to check the derivative of both pieces, and they have to match. And the notation here is super important, right? So notice that my final answer, it's short and it's concise and it's correct. So I say it's differentiable because it's continuous, which I showed at the beginning. And then I showed that its derivatives match from both sides.